Hello and welcome to the next group of recorded lectures on continuous random variables and probability distributions. This is Dr. Leslie Ann Asmus, and we're going to kick off with just kind of an overview of this topic of continuous random variables and probability distribution functions for these different random variables. Looking back, we have spent some time going through basic probability concepts and rules. We've had a brief look at some of the discrete random variables, attributes about their mean, their expected values, and the variance for these random variables. In the general form, what is a random variable? What are the expected value and variances? We had a brief look at Chebyshev's theorem, and in class worked through some examples of that. And then we went through and we talked about uniform discrete probability distributions, binomial, negative binomial, geometric. We looked at a number of different discrete random variables and their probability distributions. Again, from previous classes, we've gone through and kind of said, okay, so most experiments, we generate outcomes that can be interpreted in terms of real numbers. And so we looked at a variety of things. You can certainly have something like a random variable that tracks the number of accidents at a particular intersection. But we could also have a random variable give a numerical value to something that is a non-quantitative. So it could be the number of students that did well, or let's say failed, did fairly well, did moderately well, did, however you classify it, and then give a ranking to those and say, okay, if a student fails a particular class, then they get a 0 as associated random variable value. If they do fairly well, they get a value of 3 or whatever. So something like this. And we looked at it from a discrete, so non-negative integer values is what we looked at. Now we're going to turn our attention to the continuous random variables, and let's look at what this goes. Again, we've talked about it, we're just extending it. A continuous random variable, x, is a random variable that can take on or assume any value in an interval of real numbers. So as the previous slide showed, you start talking about the height of something, the length of something. Not going to be a height or a length of exactly 60 inches, but it could be 60.1 inches or 60.12 inches. And so we're going to look on a continuous realm, and hence the name continuous random variables. We're going to be looking at intervals. Every value in the interval may not show up even in very large samples. However, we cannot rule it out as a possible outcome. So continuous, we might say the duration, life length of a particular TV. Is it 10.1 years? Is it 10.3 years? Is it 10.1 to 5 years? Those could all, if we went out and looked at samples, drew a sample, those are all possible values. Even 10.1257677 as opposed to, 10.1257657. Those are all to those different significant degree decimal points, possible values that we could have in a random sample. But again, even very large samples, even if we look now like going with a TV duration, life length, even if we looked at 3 million old TVs, 10-year-old TVs virtually, and we would find all these different, not even just a 10-year-old TV, just looking at all TVs. You could have a sample of size 10 million, and you still may have values for life lengths that don't show up in your sample. So that's all that's saying. Okay, so let's continue on. So we did look at some of these general characteristics of discrete random variables. We noted, of course, that the probability was always non-negative. And we have the same thing now with the continuous random variables, where for all values X in a set of real numbers, the probability that the random variable equals that value would certainly be non-negative. Again, we have, just like we had before, if we add it up, we sum over all possible values, the values a discrete random variable would take, that added up to 1. We have the same thing here. The only difference is now, and this is where your calculus background comes in, is that instead of a summation over these different integer values that the random variable could take, now we have continuous random variables. So we have to do an integration of the probability distribution function P of X. And that's going to add up over all possible values that X can take, integrate the function, and you come up with a total of 1. We're going to be looking at intervals of the random variable. What's the probability that the random variable is between A and B? That the random variable would take a value between A and B. In order to find that out, you would do an integration of P of X between A and B. And so what we're going to do is, so this is, and you may kind of go, oh, calculus, here it comes. What we're going to do, we're going to use your calculus background, but you're not necessarily going to be actually applying it to specific problems as much as understanding conceptually how calculus comes into play in this topic. This one always gets students' heads kind of twisted around a bit. So we're going to actually, so whereas before we might have said, some of our previous example, what's the probability that exactly 7 ducks out of 15 drawn will have some disease if the probability that any one duck has the disease 50% of the time or whatever. We went and actually said, what's the probability that exactly 7 ducks are infected, right? And so we gave a probability for that particular number, X is equal to 7. What this is saying here, so consider an example where an experimenter life length of a transistor is indicated to be the random variable X, can consume an infinite number of possible values. And what we're going to actually do is you say, well, what's the probability that a transistor we are using will last exactly 497.392 hours? This is different than the discrete. If we assign a probability to that, we won't actually be assigning probability to that specific number. Because what happens is, again, we want all the probabilities to add up to 1 in the integration. And even if we say that we're going to assign it a very, very small number, because as soon as we say 497.392, then we could have a transistor have a life length of 497.3921, 497.3922, and so that extra significant digit. And then we say, well, how about making a smaller probability? And so you say 497.39221. So you keep going out in those, the number of significant decimals, and you get yourself in trouble to get all those probabilities to add up to 0. So the way we work with this is to say that's where we're working with the intervals. We're always going to be working between A and B, right back here with 0.3 on the continuous. We're going to be talking about what's the probability that the random variable falls between 397.1 to 397.5. And by doing the interval, we can do an integration on that P of X, and we're not going to get ourselves into trouble making sure that 0.2 is not satisfied. All right? So we're going to assume a probability of 0 to a specific value that the random variable could take. That doesn't mean that that particular value can't happen in real life. It just means that mathematically we need to do something with that because we want all our probabilities to add up to 1, and that's the way we handle that. We work with intervals. Okay, so what does that integration look like? Was integrating between A and B, the function P of X, look like? And this is similar to what we were doing with discrete random variables with a histogram, and we said, okay, we would add up the area of the two rectangles if we were interested in the probability that X is either 5 or 6. Recall that what we were doing was we would add the area associated with that those two pieces of the histogram to figure out that probability. In this case, what we have is you see the P of X along the vertical axis and X, the random variable values, along the horizontal. And the function is just as this curve, and you see the area is just what that integration is. That striped area is the integration under the curve between A and B. So that gives you the probability that X, the random variable, falls between A and B. Similar to what we had before with the cumulative distribution function, we had, okay, add up all the probabilities, summing it for a discrete random variable for all values t that is less than some number b to find the cumulative distribution value associated with f of b. Now, again, we have continuous, so we're integrating all values from negative infinity to positive b, assuming your random variable can be negative value, or, a lot of times it'll be just between 0 and b in this case, but you're integrating that function. Expected value, recall in a discrete, again, summation versus integration. That's the key difference you see here. If you look at what's going on between the discrete and the continuous, very similar, right? You take the values of x times the probability of x. In this case, we're doing the same thing in the continuous, but we're integrating values of x times p of x. And you integrate between between negative infinity and positive infinity. Or however the integration would happen, however your random variable, what values it can possibly take. Same thing with the g of x. We noted that if we were interested in e of g of x, that was equal to the sum over all values, possible values that your x can take, the random variable could take, of g of x times p of x. And so recall we had examples where we said the cost was 10 times x, x being the random variable, the number of whatever was happening. So 10x was g of x. And we said, well, what's the expected value of the cost? Well, that's all the different possible cost values associated with the different values of x times the probability of x being a specific value. We're doing the same thing. Look at the continuous random variable. It's very similar, right? It's just g of x times p of x, but now we're integrating instead of doing a summation. Variance, similar kind of thing here. On the discrete, we did summations. What we're doing on a continuous is we're doing integrations. If you look at these two formulas, to the top and the bottom, they're very similar. It's the same intuitive, conceptual idea in terms of the variance, the spread of possible values that can happen for a particular random variable. Previously, we looked at discrete random variables and noted what if that g of x has a linear relationship. So what was the expected value of g of x when the g of x is linear ax plus b? Then we said that that expected value is equal to a times the expected value of x plus b. The variance of ax plus b was a squared times the variance of x. Standard deviation, just took the square root. All of this applies, even though we've moved into the continuous random variables. Chebyshev still applies. You can still determine, work with Chebyshev as the theorem to give a general framework of what's the probability associated with so many standard deviations away from the mean.